Welcome, Hornets, and thank you for coming and taking a look at what I have for us today. We are looking at the second part of the worksheet that I gave you for the holiday. For those of you visiting, you'll notice that we have the four questions on the document camera right now. So I recommend that you take a quick screenshot if you're visiting. If you have the worksheet, please make sure you have it out. Otherwise, I'm going to go through these problems. I'm going to read them first, and then we'll go through each one separately. Here we go. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 6 centimeters per minute. How fast is the area of the pool increasing when the radius is 9 centimeters? A spherical balloon is inflated so that its radius increases at a rate of 4 centimeters per second. How fast is the volume of the balloon increasing when the radius is 4 centimeters? A conical paper cup is 10 centimeters tall with a radius of 20 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is the water being poured into the cup when the water level is 2 centimeters? A hypothetical cube grows so that the length of its sides, s, are increasing at a rate of 3 divided by s minutes per second. How fast is the volume of the cube increasing when the sides are 8 meters each? Alrighty, so let's go ahead and begin. We're going to take a look at the first question, number 5. Water leaking onto the floor forms a circular pool. So if I'm looking at a circular pool, let's make sure you can see this. Drawing a picture will help me to understand that as this radius grows, it has to have a positive rate. The rate that they've given us is 6 centimeters per minute. So we have a positive, r prime is 6 centimeters per minute. We are also told to find the area of this pool, and we know that the area equals pi r squared. And our area, our radius, is supposed to be 9 centimeters. So with that, what I intend to do is take the derivative. This is our implicit differentiation. A prime in terms of r is equal to 2 pi r prime. I always like this because I can see my circumference there. There's a direct relationship between the rate of change in our radius and the circumference of the circle at the moment of r. Isn't that neat? All right, let's go ahead and keep going. We're now going to plug in the values that we have. Our a prime is what we are looking for. So we have 2 pi times 9 times 6. And you'll notice this is centimeters per minute, and our units are going to end up being centimeters squared per minute. And when we multiply, depending upon whether you have it in terms of pi or not, that's what I'm going to call it. It is 108 pi centimeters squared per minute. And that's my answer for number 5. Number 6. Number 6 involved a spherical balloon. Let's just take a look at that again. A spherical balloon is inflated so that its radius increases at a rate of 4 centimeters per second. How fast is the volume of the balloon increasing when the radius is 4 centimeters? Now, the hardest part about this is reminding yourself, what is the formula for the volume of a sphere? And you'll notice I always start by drawing my picture. Here's my radius. The radius is increasing as the balloon is inflated. So we're looking at r prime is a positive 4 centimeters per second. Notice how I always start by thinking about whether it's increasing, growing, getting larger, or decreasing, getting smaller, shrinking, because those represent the positive versus the negative rate. Alrighty, so our formula, if you don't remember, it's 4/3 pi r cubed. And if you don't recall, please be aware that these are the formulas that would be given to you on a test or an AP question test. We're now going to be finding v prime, implicit differentiation, and we end up with 4 pi r squared r prime. We're now ready to plug in the r prime equaling 4 centimeters per second and our r, which they gave us, was 4 centimeters. We're then going to have v prime equals 4 pi times 4 centimeters squared times 4 centimeters per second. That's going to give us centimeters cubed per second, or cubic centimeters per second if you prefer. Once again, multiplying this through, I end up getting 256 pi. Once again, this turns out to be just 16 times 16, or 4 to the 4th power, and that is 256. Our next question, question number 7, is dealing with our cone again. Now, we've seen cones before, so we have to be a little bit more careful because we know that just like with our optimizations, there's a linking formula that allows us to convert our radius into heights or our heights into radius. And this is by the proportion. So once again, I'm going to start off by drawing my picture. Here's my radius. This is forming my similar triangles. And according to the information, let's just go to it again real quickly. A conical paper cup is 10 centimeters tall with a radius of 20 centimeters. That'll give us the proportion. The cup is being filled with water so that the rate of water rises, or the water level rises, at 2 centimeters per second. And we're trying to find the rate at which the water is being filled. This is our volume prime at a level of 2 centimeters. So we're looking at height. So we have a height that is 2 centimeters. We have a height prime. The water level is rising at a rate of 2 centimeters per second. We're looking at a radius that is 20 and a height that is 10. Now, keep in mind the units are currently all equal, but if the units weren't, we'd have to do a conversion of units somewhere. The formula that we are working with is volume equals 1/3 pi r squared h. Notice we have two variables here. That's why we need the linking equation. So here we go. Let's do our radius is to height as 20 is to 10, and this gives us r equals 2h, or h equals 1/2 of r. Now, once we have this, we can now go back to this equation. Remember, we wanted height. That's what we're given here. So we want to replace our r with height. Volume is then going to have to equal 1/3 pi r squared, and this is what we're replacing with 2h, times h. This gives us 1/3. Multiply that and square it. You'll notice that's going to give me a 4. 4/3 pi h cubed. All righty. We're now ready to take our implicit differentiation. V prime is equal to 4 pi h squared h prime. And I can now plug in my information. Remember, our information's right up here. H is really 2, so I have 4 pi. I have a 2 squared, and I have another 2. The units that we're looking at are centimeters cubed per second. And when I multiply all of this, you'll notice I just have 8 times 4, and that's 32 pi. This brings us to our last question that we have on this worksheet. This last question is a very straightforward one with a cube. Let's just read it again. A hypothetical cube grows so that the length of its sides, s, are increasing at a rate of 3 divided by s meters per minute. How fast is the volume of the cube increasing when the sides are 8 meters each? Notice, this is going to give me the rate of increase of s to be 3 divided by 8. So let's go ahead and make our picture and set this up. So don't get frustrated by the cube. Just draw a close facsimile. Remember, the sides are growing. That's really what we want to make sure that we see. Going up, going out, and we also have going out this way, or if you prefer that way. Now, we know that the volume of a cube is going to be the number of sides cubed, and we also know that v prime would have to be 3s squared s prime, and we've already identified that our s prime is going to be 3/8. And once again, this would be a rate of meters per minute. And we're looking at s at that moment in time when it is 8 meters. So we're plugging in our information. V prime is then going to be 9/8. Let's try that again. Let's just put it all in first, shall we? And then we'll multiply. So I've got my 3, I've got my 8 squared, and I've got 3/8. First of all, notice that the squared is going to reduce with that 8, and you're going to have 9 times 8, and our units will end up being meters cubed per minute. So we end up having 9 times 8. That is giving me 72. And I'm left with 72 cubic meters per minute as my answer. Alrighty, I hope this has helped you to see how we do these problems, and I hope that you have already tried them before doing this so that you get the true experience. Thank you very much, everybody. Please be safe, take care, and have a wonderful day. And remember, it's easy to be mean, so try to be nice. Change starts from within. Thank you, and goodbye.